Thanks for sticking around with us. So if you haven't missed the end of this session this morning, I'm Stefan Maldini and lead of Project Reactor at Pivotal.
And I'm Ryland Degnan. I'm the CTO at Netify. So yeah, thanks for coming to this session. I'm super excited to be here with Stefan to talk about the Reactive Endgame, RSocket, and how we envision the future of systems architectures. So communication in the cloud is a challenge. This is a quote from a recent CNCF conference. The network is the unsolved problem of the cloud and open source. We need the network to be a first-class citizen of a cloud system. So enterprises today are in this transition state from this relatively constrained environment of the data center and sort of well-understood networking model to this wild west of the cloud. And it's becoming increasingly apparent that old approaches to networking no longer work in this new world. And I've experienced this firsthand. So prior to Netify, I was on the Netflix Edge platform team, where if you imagine Netflix as a sort of giant hourglass with 100 million users and hundreds of different device types funneling traffic, and then fanning out to hundreds upon hundreds of microservices within the back end. The system that I operated and owned was sort of in the very center of that hourglass. So I've pretty much been firsthand witness to every sort of different ways that distributed systems can go wrong, can fail. When you get configuration wrong, when you get paged at 4 a.m. and have to go in and sort of rescue the system from failure. And that sort of leads into this next quote from the same conference. A standard approach is needed to sort of connect and communicate all the different pieces in the distributed applications that we build today. And that idea was sort of the genesis of RSocket within Netflix and then in collaboration with Facebook and Pivotal, this idea that you can define a standard to solve these sort of common problems across your architecture. So RSocket is an open source application layer network protocol. As I said, it was developed in collaboration with some of sort of the vanguards of moving to the cloud, and from experience, sort of everything that can go wrong when you build distributed systems. So RSocket simplifies communication by providing this common unified API across all different interactions. So as Steve pointed out in the keynote just now, RSocket is transport agnostic. So it gives you a common layer upon which to build applications that's underneath which you can switch out sort of the transport layer and without making any code changes. And more than that, RSocket was built for modern cloud applications. So on top of being transport agnostic, RSocket provides solutions for these common problems that you encounter again and again when you're building distributed systems. So things like session resumption, your connection drops, how do you sort of resume the state of what was going on? Fragmentation reassembly, so why should you use a different network protocol to transfer gigabytes large files or tiny chunks of JSON? And then things like predictive load balancing, so that the client engineer doesn't have to solve the same problems again and again. So what characterizes a modern cloud application? Well, as Stefan did a good job pointing out, I think there's sort of three things. It's distributed, heterogeneous, and interactive. So gone are the days when we built these sort of monolithic, fat web servers and have a thin client that just sort of makes a request reply and consumes the response. Today's model is much more interactive, and it's also much more heterogeneous. So it doesn't just exist as this client-server model. Compute is distributed throughout the entire network of the application and across many different types of clients, platforms, and languages. So some modern applications have to be aware of the differences between things like browsers, phones, gaming consoles, set-top boxes, and then all the sort of different back-end infrastructure and topologies that you might want to take advantage of. So one way to sort of visualize this is this three-dimensional axis of complexity, which represents sort of this explosion in complexity that's taken place within the last several years. One axis being its deployment topologies, where your application is deployed and how. Another being this set of platforms and frameworks that we interact with. And the third being the set of protocols and interaction models that have extended far beyond sort of the request-reply model of HTTP and now includes sort of the bidirectional streaming interactions. So with that, I'll hand it over to Stefan to talk more.
Yeah, so especially we know at Pivotal that the multi-cloud story is a thing. We see more and more hybrid use of different cloud platforms because some cloud platform will provide feature A and B, and the other one is going to provide service A and B. Different ones, you will choose, according to your business use cases. And also, we know the story of hybrid cloud between the private deployments on-premise and also the deployment on public cloud as well. So the boundary between, where your applications sit actually is getting more and more blurred. So that's technically a challenge, and we have 10,000 networking solution to deal with this problem. There is also the explosion of orchestration platforms. So platform A and B, Azure, Kubernetes, etc. They're going to do something that will be different and will be on a different set of instances as well. They will be separated by network boundaries too, and it's something complex also on the framework side, because you will have part of your enterprise using JavaScript, hopefully a large part of the enterprise using Spring because they are sane people, and some crazy people will use C++. But in this world, we still have to connect together. We still need a standard. HTTP, in some aspect, is pretty nice in giving a kind of well-defined protocol. So we know what to expect from HTTP. It's just very limited in what it gives you. And we have built everything on top of that. That's another problem. So if we used all of this platform, for instance, now if you take a step back and see again, look at the picture of what kind of interaction we have today. Okay, we have classic application from Spring, for instance, serving HTTP, HTTP2 request. So request reply typically, most of the time that's what people are dealing with right now, and maybe also driven by the fact that people only use HTTP as well. Then you have devices and IoT and all these kind of use cases. Devices connecting directly to your backend. So you might use, for instance, Spring Cloud Dataflow and Spring Cloud Stream to ingest data from different sources than HTTP. So that's another cool thing. We know already in Spring that there is not only HTTP. There are other models you want to deal with. And you will use that for kind of different interaction. You will stream data here. And then you have also, new devices, games and console in that case, that will interact with backend servers. And, in that case, if it's a game, like a physics game engine, there will be C++, and the interaction will happen over a network with maybe something like gRPC. And you have this RPC interaction model then, where you are very contract-driven, generate stubs, and, you don't really care about thinking about how the client interacts, especially when you're in the game development. You really want to focus on game engine, for instance, and not really on how things communicate over a network. So that's this kind of interactions, and then it can go even very crazy between a desktop and mobile application. Think about Facebook chat, for instance. You are on your phone and you're communicating with friends on the desktop, slacking at work. And they do that in real time, transparently. They are also, phone and communicating with console because, they play the same game. It's becoming more and more a thing, like Fortnite, for instance. And they're communicating as well, like in a peer-to-peer fashion. It's kind of messy, and I think that's where we come to with RSocket. Can we really do something about that?
Yeah, I think on the face of it, this really does present a challenge, sort of all the different things that we want to accomplish in a modern distributed application. And it's important to think that there's different things you could try to do about it. And some will be more successful than others. There are some that I would argue that you really can't do anything about, and one of them is this deployment topology. So you could try to restrict the complexity of that access by imposing some sort of uniformity of infrastructure. Say, As a company, we're going to deploy everything to Google App Engine. All of our code is going to be written in Python. We're going to use these set of approved libraries, and everything will be great. I would say that almost guarantees you're going to have to completely rewrite your application within several years, as many companies have found out. So there's a cost to trying to impose uniformity of topology. And there's also sort of things that you can't do anything about. If you're deploying to a mobile phone, you're using their platform. If you're deploying to like a web application, you're sort of constrained already. And if you try to do, you could try to do things like run all of your code within sort of Kubernetes or containerize everything, but there's going to be cases where that's not possible, like a legacy data center application that relies on certain properties of the data center, or again, it's a web application or a mobile application. If you try to put, say, like a sidecar and everything, there are deployment topologies where that is not possible. And so any real solution to this problem needs to span all deployment topologies. I think another thing we can't do anything about and really don't want to is this proliferation of development frameworks. This is something kind of we found out at Netflix. Most of the platform was Java, but there was a growing number of people who wanted to write Node backends for their web applications for very good reasons. And if you try to sort of impose, again, a uniformity of development frameworks, you're missing out on a lot of the promise of the cloud. What you really want is to be open to new technologies and allow developers to choose the right tools for their job. The good thing is, there is a small and sort of finite set of these interaction models, which is the third axis of complexity. And that is small enough that we can sort of try to impose some sort of standard on top of which we can greatly simplify the way our applications are written. And again, that is sort of the origin of the RSocket story.
Yep, and without getting too much into details, now it's time to see some kind of contract, how it looks like in a closer fashion. We have a nice contract, as you can see, if you're familiar with Project Reactor. You can see the types or normally it should be familiar to you. The contract defines clearly 4 interactions. This morning we presented these 4 interactions. That's exactly the contract, at least in Java, how it looks like. And every language bindings like C++, JavaScript, they all will have the similar contract implementing given the language capabilities. So here it's cool. We on the Java side we can use Reactor. So RSocket Java, the RSocket project on Java, deployed on Maven. You can actually use it directly. Depends on Reactor to provide you this experience. It's actually, this solution we find elegant to solve a lot of problems. This morning we mentioned a few of them. I think one particular I like to highlight is the problem of, you on your iPhone or Android device crossing the road, especially in the US, I find you have a very spotty connection and you lose your connection while you were chatting. And then your phone reconnect again to a different cell tower, for instance, or Wi-Fi, and you get the connection again. And having this capability of having a session ID, basically, that will automatically be retransferred over the network and give again the ability to the backend to not recreate all the state for a given client, but just do the delta, because they know this is the same session that disconnected and reconnect. This is what Steve this morning mentioned, and what saved a lot of cost to Facebook, for instance. And that's pretty cool, I think. It's, another interesting thing is we don't really care about where applications are deployed. And really, that's what we're going to demo just after. You have to see to believe. I don't sell often this kind of word. I don't like silver bullets, but I've been really surprised by the flexibility of the protocol. It's basically level 7 if you think about layer of protocols. So it's a framing thing, and it works on top of anything. So anything you can connect, use to connect and establish communication, data transfer. TCP, UDP, as we've seen this morning, WebSocket, we're thinking about more. It could be even a message broker like Kafka. We don't really have assumptions on how this data payloads and headers and metadata are going to be exchanged. They just have to respect a certain behavior that all the RSocket driver are going to implement. So in terms of Java, again, if you if you start using RSocket, it will look like that, basically. There are multiple transport registry or transport library you can use as an option. That's the TCP one. It's using the same factory, but you pass this transport directly in the factory. You can see the use of block, obviously, for some simplicity reason in this slide. You'll see. I will use this to get a reference to RSocket. Remember, RSocket is the contract with the 4 interaction defined. So directly what I can do with this 4 defined interaction, I can just use one of them, the request-reply interaction, pass a payload, which I need to build, and do something. And when it's successfully complete, I can interact with a callback in the classic Reactor style. I have obviously masked the part where I pass data to the constructor of default payload because it's just something you don't want to see. It's basically byte buffer creation, and in terms of, it's using native byte buff, so it's pretty efficient. It's pulling byte buff, but you really don't want to see it. And what you think about that is, oh my God, it's basically very low level. You don't want to deal with bytes. You just want to use it, and it's pretty scary, but you can use it. It's pretty low level on purpose because it gives the ability for everyone to build something on top. And the abstraction, the core abstraction, is isolated and do one thing and one thing well. It doesn't try to do more. Then we have side projects, pet projects, built on top of it. If you want to reduce the complexity of using such thing, you might investigate RSocket RPC, which is the first implementation using, in that case, protobuf to be contract-driven and not deal with all this mess, like byte buffer creation, but deal with message you pass, standard messages you pass around. And basically, when you start using RSocket RPC, the code is basically much simpler. You instantiate the service generated by protobuf, and you have great plugins and Maven to do so. You call the methods generated by the contract here, records, and it's generating directly Reactor code. So the return type of record is really going to be flux, and you pass, like in that case, you will pass a Scala object, a request, and as a result, you get a flux, a stream of record, which is translated in Java, a flux of records. The cool thing about this RPC thing is it's not only about Java, it's about other stuff. So yeah, I'm hiding the RSocket part. We just created that a bit earlier. That doesn't change. You still need to create an RSocket reference. It's just the interaction that is simplified here. But the cool thing about that is you can generate JavaScript code as well, which is pretty awesome. It's not only working on Node.js, it's also working on a browser, which is cool. You don't need anything. You can just use that as a dependency in your browser, and instead of using WebSocket to interact with your backend service, you just use the generated code by RSocket here, and that's replacing basically what you did directly, manually with WebSocket, for instance. And that's basically similar to experience also to what you have in Java. You have a request, you pass directly to record, and as a return type, we have a companion object named Flowable. It used to be another name, but we use right now this one because it's a simplified version of what we do with Reactor. We think about doing a Reactor code JS version as well, but right now it's something you can, like in Reactor, subscribe to, do map and this kind of interaction you have in a Flux API. So pretty similar. You do that in a browser or Node.js. I emphasize on that point because if I think about, for instance, gRPC doesn't do that on a browser. It does do that on Node.js, but you can do that simply with the browser, for instance, unless you start tweaking around things, and there are projects right now in the pipe. But some might still say it's too low level again, and basically you have still hidden the configuration of RSocket, and you still have to do that. So if it's too low level, is there something we can do about that? What kind of level is next then after that?
Yeah, so if we flip back a couple slides, I think the complexity that's hidden here is the creation of this RSocket. And if you think about what that entails, it still involves sort of some kind of service discovery mechanism where I need to know which IP addresses I can associate with this service. I need some way to go and fetch them and then load balance across them. And that's a lot of complexity for the developer to continually manage. But at Netlify, sort of we created the next generation of infrastructure to sort of put this complexity onto the network layer. And this is where I think RSocket gets really cool. And this gets to the heart of why RSocket is a protocol and not just a library. Because what it allows you to do is take this standard protocol and put the complexity onto your network instead of your application. And that's immensely powerful. As you know, a company in the 80s discovered they could make a TCP router and sort of offload all this complexity. That company is Cisco. So this idea of sort of offloading complexity onto the network using a standard protocol is really immensely powerful. And so what we've built at Netlify with Proteus is sort of directly analogous to a TCP router, but instead of routing to IP addresses to machines on your network, what you care about as a sort of modern application developer is services. So Proteus does easy routing to services and devices. So nowhere in your application code do you ever need to worry about an IP address. And then in addition, it's got all the built-in advantages of RSocket, so you get flow control. It also offloads things like load balancing to the network layer. So nowhere in your application do you need to load balance to a bunch of servers. You just send the request to the network to this virtualized connection, and it'll allow the network to discover the best path to that service. And so what this allows you to do is essentially get rid of all of the complexity from your client-side code. So instead of creating your own RSocket, you can just add an annotation in Spring, inject a service to the client that you want to talk to, and it will create a virtual RSocket to this group, Spring 1 demo records in this case. And as machines that offer that service come and go from your network, it will automatically adjust load balancing to give you the best path to that service. So I mean, yeah. This is truly all code is gone. I think it's completely application driven. You can call that
I feel happy now.
Spring Boot. So that's cool for the developers. Let's dig down a little bit and see what is actually going on under the covers there. So Proteus works, you do deploy it much like a TCP router. There's very little configuration. You deploy it into your network. They sort of self-discover and cluster these nodes within this broker cluster. And then into that cluster, you can connect things like web browsers or mobile phones. And immediately, sort of without even any back-end presence whatsoever, these devices can start to talk to one another. This is sort of the peer-to-peer model. And the brokers cluster together and exchange information about who's connected where in the network. So very much like TCP routing, you don't need to know the entire state of the network in order to send a message. I mean, it'd be silly if the internet worked by every node on the internet needing to know the IP address of any other thing on the internet, right? It's designed to scale, so it can't work that way. And then on top of that, you can start to connect in your microservices. So you might have a microservice written in C++. The next year, you might decide to rewrite that in Node. You can just swap it out under the covers with absolutely no changes anywhere else. And then, in addition, these services can call out to clients, or what would previously have been called a client, so a web browser. So a web browser in this model can function exactly like a back-end service. It can offer its own API that can get called from your data center. And it does more than just services. So into this network, you can insert things like an open tracing backend. So every Proteus client is automatically instrumented to start dumping open tracing information. But because of flow control, nothing actually flows through the network until there's a backend within the network that's capable of ingesting and handling that traffic. Likewise with the metrics backend. So you can just start up a Prometheus server, connect it into this network of services, and instantly it starts dumping metrics information that you can then go back and analyze. And like I said, unlike sort of an infrastructural or something that's trying to standardize your deployment topology, Proteus is designed to be almost configuration free. So it is very much equivalent to just installing a TCP router and making it part of your network. And unlike sort of something like Istio, which has dozens of moving parts, I think like in excess of 30 maybe last time I checked, there's only one moving part to this, and that's the broker. And you can run the broker just by running a Docker container. You can put it in Kubernetes, or you can put it in your data center or bare metal. It's very flexible in terms of where you actually deploy it. And beyond that, there's sort of this Proteus PCF service is coming soon. So shortly, even that small amount of configuration will be gone. And you'll be able to deploy this just simply by clicking a button in PCF.
Yeah, CF push basically, and the binding. Pretty cool. So we are going to do a lot of demo, or all demo with the time we have left. And this demo is a simple kind of tournament use case. So you will see Marvel superheroes fighting each other, or basically virtually fighting each other. The way we're going to do that is we have 4 microservices. Well, yeah, 4, including the client, because there is no real backend application. Everyone is a kind of a backend. And one is going to be tournament, calling depending on the records and ranking. So calling records, which is a R2DBC-based microservice, pulling records of superheroes from database, and giving that back to a tournament. Then for each pair of superheroes back, we're going to call a ranking service, which is going to choose between 2 who's winning. And right now, the Java 1 implementation is deciding to do so by selecting the one with the most superhero stories, super stories. So Superman has a lot of stories. For instance, if you make him fight with, I don't know, another superhero not well known, I don't even have one in mind right now. Maybe Magneto, for instance, or even this one. Anyway, one superhero not very well known. I've seen one called Captain America Chavez. I didn't even know this one existed. Raise your hand if you know this one, but it's actually a superhero. And yes, so Superman will win in the ranking service and go back to tournament, and then give this information back to a client, getting access to this tournament. And in fact, a tournament works this way. You have, these pairwise fights, who has the most stories, and then we have the winner, so it's round 2, and then we have the final winner out of these 2 semi-final winners, which is the round 1. So that's basically the big principle of this demo. And let's just try to do it right now. I'm going to switch to IntelliJ. So let me zoom a bit and start things. So interestingly, I have my I can zoom down. I have my 4 applications. I don't know if you can really see them well. They are all terminated right now, brutally terminated, as you can see. But they are the 4 applications mapping with what I've just shown you. And another interesting cool thing about this kind of Proteus-based architecture is there is no order, preferred order I need to have to start this application. I can start any of them in any order I want. Basically, information are going to flow. So let's look at the client, because that's the simplistic one. If I look at the client, it's a simple Spring Boot application. And it has injected this generated RPC, protobuf generated client, which is tournament service client. So you can see it's really generated. It's like, yay, generated code, love it. But if you know gRPC, you know this kind of code anyway. You don't need to deal with that. You can just inject it like it's an auto-wired dependency. And this is a client runner, so starting with the application. I'm going to build a request for my tournament service and start a tournament. And in this case, I'm just going to do a tournament forever. So in that request, a tournament will have 40 challenges. and they will fight each other. And at the end, I shall have a super winner. To get this super winner, remember it's a Flux. I have all these nice API, including 2 iterable, which is a blocking way to consume Flux. But I don't really care. It's a client. So I can just do that and start this client, and there is nothing else started right now. So just starting the client. And I should have, at some point, when the service is available, I should have, at some point, things printed like in this logger info here. So I'm just doing that, when the round is the first one, that means it's a final round, so I'm going to print the winner. It's connecting to my local host, which I've started. So remember, I'm going to actually do it again because it's quite fun. To start a kind of mesh here, I just need to do that, which is one Docker instance with a Java application based on Spring and Reactor actually native. And starting, and it's going to be like the broker thing where everything is connecting to. There's nothing else, no other tricks. So I'm starting that, and I'm restarting the client. I just stopped, so starting again. It's
worth knowing there's no code in here to block and wait until the services are available. So it's trying to send this information, but there is no back-end services that have been deployed yet. So the client is sort of completely disconnected from the back-end services. So normally, if you're doing this with HTTP, you'd start getting errors again and again. So it's an endless stream of errors. But it's simply waiting for that service to now be available.
Right now, by default, it's using TCP. So these connections are established directly with TCP. I could have used something else, and we see something else. Now let's start the backend service. So the first one I'm starting is the record service, the one connected to the backend database with Spring Data JDBC and the R2DBC support. So how it looks like, well, you've seen a bit of code this morning, but it's just like that. We use a non-blocking PostgreSQL driver via R2DBC. We generate the query we want to do when we call this method, classic Spring Data code. And then, we return a flux instead of returning a list because we're going to stream the result back. And when we are ready, remember, now the protocol is going to send a back pressure from the very end, the client, to the very upstream component. So if the client is slow, remember this morning the small request going on the diagram, and then the data flowing back to the client. That's basically the same thing. The client will say, okay, I'm slow, I'm printing things, I'm maybe doing a thread sleep in my client runner. So the requests generated and propagated across network are going to come in a very slow rate, and this is going to stream data from the database in a slow rate, giving more space for maybe a faster client. And it's about being smart and schedule things, reward things that are faster to consume data. So your server is mostly all the time available. It's not impacted by a slow client, really.
This lets you do crazy things like you don't have to define a paging API for your database, or you can just return a flux. The consumer, because back pressure is propagated all throughout the chain, can just request more records as they're able to consume them. For instance, in a web application, as the user scrolls down the page, you can just say, hey, give me 2 more, give me 10 more, give me 15 more. And that message will propagate all the way to the database, at which point it will just stream the records back to you.
So the cool thing is we now implement also the generated contract by protobuf. So it's contract-driven, all this thing. So again, recognize this kind of code. It's not that ugly, but still, it's generated stuff. And again, it's generating Reactor code, so pretty cool for that. And that's, a receiver side, so it's an interface, classic like in gRPC, you implement it, and you implement the method. Here I'm going to stream records given a record request. To do so, first I'm going to retrieve from the repository the total number of superheroes in my database. I'm going to cache that result. So it's not actually doing that in my constructor. It's going to do that one time and then cache the result. That's why in the record method, I do total, and then I log, and I transform this total, given the count, into a list of 40 streamed superheroes. I give that with the offset, given the total, obviously, and how many results I want to stream. So I'm doing that, then I map the record from the database, so classic Spring Data thing as well. I have a component, an entity I will save in the database, and I have a builder to build the record for protobuf, and that's it. In this record, I will have basically the information I need to have to transfer over the network, and protobuf, serialize everything for you. So I just do that here. I transform this record, the entities from database to protobuf records, and I stream that back, and that's it. Pretty much it. I had even a simpler version here, but every time it was getting only the first 40 superheroes, so it was a bit boring. That's why I added this count, this total, to randomly select somewhere in this total where to start the offset, basically. So that's this service, streaming records, so superheroes. And now let's see the ranking. The ranking service is super simple. So every time it's a one class thing, basically. Huh? It's not very complicated. Default ranking. And that's the ranking service, even simpler. So again, protobuf implementation, contract driven. I implement a rank method, and this one will have to choose between two superheroes, and you see the comparator here is simply compare given the story count. How many times you've seen Superman in a Marvel comic, for instance. And the winner is sent back as a ranking response, and now you see it's a mono. That interaction is what we've seen as request reply. That's mostly what user tend to use because they are not used to streaming interaction modes. So pretty simple. Again, every time the properties will look like the same. It's using localhost and my Docker image I just started. And the last one is the aggregator microservice, the default tournament service, which is a bit more subtle because it does generate these fights and basically do this what you've seen here. But in reactive. So it has called these two services and one depending on the other. I'm calling the record service here in my tournament method. Again, protobuf contract I implemented. Implement record service, stream the records from a remote database service, and then generate the tournament. So for each pair of record, which is basically what I do in round here, each pair of record, I'm going to create, to call the ranking service and generate this stuff here, the ranking result. Interestingly, the ranking, we'll see the reason for that soon, but the ranking has a timeout here, and you'll see why, but you don't necessarily need to use timeout, etc. You just call the ranking service, and it gets a result back. So let's start all of them. I still have the client waiting for anything happening.
I think the details of this code aren't important, but what Reactor allows you to do, which is really cool, is construct this whole chain of like fluxes up front before anything has actually flowed through the system. So before it's retrieved a single database record, sort of wired up all the tournaments such that the round winners each compete against the next round winner. So that happens once up front, and then traffic is able to flow through that very efficiently.
Yep. Remember, I left a repeat. So basically, I'm stopping the scrolling here because it's going to do that in loop. But you can see the round going back to the client in the for each loop. And after each round, we get closer to the round one, the final round, and we have the winner at the very end. So basically, given the story counts and random selection of superhero from the database, we give back, if I can do that here, I'm flooding actually the application. So if I can stop it, if I have control back, I will be able to see one of these superheroes. Actually, I'm printing so much things with the repeat that I think I killed IntelliJ. But the interesting thing is, while it's running or trying to stop, is I also have in the record application, the one connected to my database, I also have, it's done. I also have an interesting thing, which is support for micrometa added. And let's look at the build Gradle quickly for the record. And so you can see the dependency I use in my record microservice. I use R2DBC and Spring Data, the latest, very latest one, you know, fresh out from the oven. Then we use Reactor Core, the latest release version, and an update for Netty. But more importantly is I use Proteus, Actuator, and WebFlux to distribute these Proteus statistics, you know, the Actuator endpoint. So that means if I go to, was nearly actually spoiling the end, but if I go to Actuator/Proteus, I'm connected to Proteus stats from this application, and RSocket Java is lucky to implement, you know, metrics using micrometa. So Spring Boot sees that, takes the same registry, or actually the registry is propagated to RSocket, and the stats, you know, are using micrometa to be distributed then. So if you have something nice like Grafana, which you've just quickly seen, I started that already, and you do your nice dashboard, you know, it's pretty simple. We have a script template to do this kind of thing. You will have already, you know, for something as new as RSocket, already kind of visibility on what's going on. And you can see the heat map, you know, it's all kind of Prometheus statistics and language use. So it's a bit boring to see the query, but if you look at this one, basically it's the kind of metrics, you know, query you will write in your Grafana instance to display this kind of thing. All of that to say, there is a very interesting metric support already available. I would encourage you to have a look at that. You know, it's pretty awesome. So I'm going to actually change one thing. So you see here, I use this localhost instance, and we've seen we could use something else. We could use a remote broker, for instance, a pre-deployed broker somewhere in the cloud, something that you can yourself access. So if we go back to the slides, one thing I'd like you to do is just simply going to this URL, spring1.netify.io from your mobile phone or from your computer if you have one right now. It should look like, this. So pretty blunt, you know. It's, you know, we're not clearly JavaScript developers or UI developers, but you should see that, waiting for ranking request, and that's pretty much it.
So we're now going to do what they say never to do, which is a live demo over a hotel network with audience participation.
Yes. Oh, no, actually I'm on the Spring One platform, but we'll see. Maybe it's as crowded as the guest, I suppose, to actually, the hotel guest network.
So what's happening here is using the exact same protobuf. We've generated the JavaScript code, which is served on this web page and now running on each web browser that visits this page. And it's now going to replace the sort of programmatic comparator that was implemented in Java. So we'll kill that service and not run that at all and allow that service to be completely fulfilled by web browsers.
Oh. Yeah. So changing all my property, yeah. So now I'm connecting to a remote one. Just checking, I need to obviously restart my application. And just to save my memory, because my poor laptop is actually asking forgiveness. Like I have 3 Docker images and 4 Java applications, and you know, it's crazy. I'm just going to shut down the local Proteus instance at least. I don't need it anymore. So let's start again, and this time we will register to a remote endpoint.
Change the repeat, actually.
Oh yeah, the repeat too. Sorry. Command runner. Client runner, sorry. So remember, it was flooding the backend because I specifically said just flood the backend here. Like, if I don't even have a backoff, it's going to repeat as fast as it can. I'm just going to remove that for the next one.
Do you have the one that just calls the comparator directly?
And this service, this backend service that was doing the simple comparison, I don't want it to be this service. I want to be the audience to actually do the comparison. So you are going to be the service. We're doing the reverse automation of jobs. You are going to be the job now and not a computer program. So I'm going to remove that from the list of the connected microservices, and you are going to all be microservices. So let's start. I'm starting a tournament, so randomly, because I asked for 40 results, everyone will have, not everyone, sorry, at least 20 people will see the result coming to its device or laptop, because I'm asking 40 results, and you have to do, if I'm lucky one of them, oh, it's already done. Oh no, you haven't started, sorry. All right, so I'm not sure I'm going to be one of the lucky 21, but all right. So I see some people are already replying here, like doing the selection. So there was a fight between two superheroes, and Gamora won this one. Another one called, interestingly, Gateway. No idea who this guy is, but anyway, Garok. It's my turn. So out of everyone connected to the audience, 20 are invited to choose between these two superhero pairwise, doing the rank service. You are the rank service comparing two superheroes. And basically, if you're not selecting in time, and that's why we have added this nice code here, if you are not selected in time, selecting in time in 8 seconds these two superheroes, you are considered a slow rank service. So we're going to generate an exception with a timeout here and retry again because you're too slow. So someone else in the audience is going to be selected to actually choose superheroes. So
the funny thing is using exactly the same load balancing algorithm as would go to sort of a Java microservice. So it's observing the latency that everybody is able to perform this task at. So if you actually click faster, you'll get more queries because it's trying to optimize to hit the best backend service, which in this case is a front end.
So enough people have clicked, and thank you for that. I know it was difficult, but enough people have clicked, and that means a winner has been chosen, the application has stopped, and I don't even fucking know who this guy is, but he has won.
Click on the URL.
Yeah, let's see who's this guy. It is, oh no, it's, wait, it's clicking all character. Even Marvel.com doesn't know who this guy is. What is he supposed to look like? What? What is
the
this
most
guy?
popular superhero, Springline.
Melvin Potter is a fictional character that appears in comics book. Okay, blah, 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 blah. Okay, super, very generic description by Marvel. Thank you so much. I don't know why this guy has won, but he has won. And yeah, you have selected it. Usually what happens is people are just like, yeah, click, click, click. Oh, there's something to click. It doesn't even matter what you're clicking. But the important thing is you've seen an example of how powerful you can be when you really use the capabilities of a network protocol. Like there was nothing, like you didn't even know my IP here. I have 3 microservices. You connected to something on the cloud. You have interacted with me as backend servers, and that's pretty crazy. I mean, nothing is doing that right now, basically. You have just, yeah, became like backend services.
And it's worth thinking about the number of things that just went on there with so little code. So there's a broker running in the cloud. From Stefan's laptop, he's started 3 microservices connected into that. Nobody knows the IP address of his laptop. Everybody connected in from their browser. Again, your browser doesn't have an IP address. It's not reachable any other way than back over the same persistent connection that it's using to connect to the broker. So then From his laptop, he's running the tournament service that's going up to the cloud, load balancing back to his laptop to hit the database, going back to the cloud, going to everybody's browser to do the comparison, and then streaming back to his laptop the results of each service to drive the next round of the tournament.
All right, so another mind-blowing aspect, especially provided by the client, the Proteus client and the starter, is another annotation you can use, so another way to select things. Right now, we have injected a client, a generated client, that will pick a maximum of 20% to do this fight you've seen, and then out of these 20, 10 times more, and then 5 more, etc., etc. So in that case, I'm going to actually ask the reply from one person. Everyone is going to receive this. Everyone will see this question I'm going to ask all of you from my laptop, and you will see this question on your phone, and you will have to answer this question, and only one person will be randomly selected to actually be the winner, the guy who, the folk who answer this question. So.
And again, this is implemented at the network level, so just by changing an annotation from sort of group, which is a load balanced behavior, to broadcast, a different header gets attached to the RSocket payload, and as it flows to the router, it understands that means I should broadcast to everybody who's currently offering this instead of just a single person.
Who's the superheroes? I can actually see it. I'm maybe too late, or someone has replied. Oh no, yeah.
Oh, you've run the tournament.
Oh yeah, I run the tournament. Why? Sorry. Restarting. Oh. My connection is closed. Oh yeah, so that basically what you should see. So one of you, everyone can reply basically, and you should select who's winning in this fight. Obviously, I'm clicking there, but no pressure. But I will be waiting for everyone to, no, actually not waiting for everyone, if I'm correct, because it's the first one who replies.
Yeah, in this case, it's a request reply, so it will behave as the first to reply.
Yeah.
If you do a sort of request stream, then you can get different behavior where you broadcast the message and then merge the stream of responses that you get from everybody.
So this is, it should be working, but it is not right now getting the response back, because I think it's still, communicating through network, through the auto network. And yeah, there are still things connecting and getting basically this question. I'm not sure if we're ever going to have actually the answer. So that's a kind of possibility you have, asking questions like that randomly to, because the network boundary is removed, you can do this kind of crazy stuff. I like the fact that there is a support for, I want to stop this service. I like the fact there is a support for Spring already that soon in the development process. One thing I didn't show, I just want to connect back to my local laptop, medify.io, replace that by local host again, and restarting the two service, commenting that. Oh, I haven't started the service actually. Starting the Docker image that will handle all of this stuff. And what I want to do, comment this command runner. I don't need it anymore. Go back to him and comment. So the original demonstration we have, and do again the repeat. So kill my machine basically, and everything is started. Oh yeah, I also need the ranking. So again, we automate the job. We get the Java backend doing the ranking now, and doing a client application run. So yay. Yeah, so a lot of data, a lot of stuff going on. Now, the Docker image comes with an interesting prototype of monitoring console here. And you will see something you have seen already, maybe in the past. Traffic also, I find it cool, so I needed to have to give a note to that thing. You will find a traffic to, the 4 microservices flowing in. So right now, if I'm correct, Visceral, this is Netflix Visceral library, doesn't really support bidirectional connection. And so you only see things going in one way. It's not really, it doesn't do the other way, basically, but you should see sometimes the other direction going on. For simplification reason, we only see one direction.
Yeah, because the Netflix architecture is essentially a single entry point, which is the internet. Visceral is written assuming that there's a single entry point. But we're working on a fork of it that understands the concept of bidirectional communication, so you can have complex graphs of microservices and still render this.
You see, my tournament is actually getting data from multiple, actually that's the opposite, that's client pushing to my tournament. So you can basically drill down to every service, pretty cool, but also you have, beside the traffic, you have access to a lot of information, just
so here,
for
in
free.
real time, you can sort of see every server that's connected in that offers these various services. And you can also go ahead and configure sort of access keys per service.
Yeah, if you've seen every time in our application properties, oh dear. Right, I'm going to just do a shutdown, you shouldn't do at home, but I'm going to force the application to fail everywhere just to stop sending data. And, yes. Cool. Yeah, so what you see every time in my application properties, we've come up with key and token, so that's what they need in the Proteus broker to identify you. I've disabled something you shouldn't do at home, obviously, SSL, just because I didn't want to deal with this shitty certificate issue that you have to trust, etc. From the browser perspective, it doesn't actually support that in Chrome if you don't do that. So if you see this key, you actually see that in my, for the demo, it's pretty cool, easy to set up because you actually see that directly passed as a Docker argument. So all of these things you can pass directly in the Docker arguments. And yeah, so I think that is pretty much it for today. I think we are ready to take questions.
Yeah, so all this code is available in the GitHub repo that Stefan pointed out. And you're welcome to play around with the broker. If you go to trial.netify.com, we can spin up a trial broker for you, or you can run it yourself as a Docker container. It's available on Docker Hub. You should be able to recreate this demo.
All right, so just one thing before I ask questions from you. Please endorse me on LinkedIn for animation, on Keynote animation. I've spent a lot of my life learning this skill. It's pretty cool. I'm proud of me, and I'm going to shut up now. So, any questions so far? Question. All right, sorry.
Okay, so have you tried with a reactive JavaScript framework like Vue.js or that kind of thing?
Yeah, Proteus has support to transform into RxJS, and it's relatively easy to do other ones.
So I would also add that on your repository, so the question was, have we got something with like React or AngularJS, something like that, I guess?
Vue.js.
Oh, Vue.js?
It's not opinionated. So we have demos using React. This one uses
Nothing, I think.
jQuery, I think. Yeah, but
jQuery and ECMAScript 6, but there is a demo on your repository, on your organization with React. Maybe there is one with Angular, but mostly for sure the chat demo you have is based on React. And you can use anything basically.
Well, the idea, is updated, then they're automatically updated. So,
Mm-hmm.
of course, Spring webflux. So I'm just wondering how to make that seamless, to where something updates on the back end, you know, like a flux, right?
Yep.
Yeah.
Flux, and it's automatically showing up seamlessly in your UI.
Yes. So that is kind of, you can build this kind of experience, you know, with a reactive client or rich client. You can build this kind of thing. In my opinion.
Can you just repeat his question? We couldn't hear.
So the question again was do we have like a direct support for UI, rich client UI libraries like Vue.js or React.js or AngularJS? And I mean, at all level, we don't deal directly with that, but it's pretty easy to integrate. There is a demo if you go on Netify organization, chat demo it's called or something like that, based on React.js, so that's one example. I think it's pretty easy to imagine a demo with AngularJS from that or, you know, Vue.js.
Yeah, the types that are exposed from JavaScript are Facebook's sort of equivalent implementation of reactive types, or the equivalent of Reactor. Mm-hmm. And those just generate events that you can consume and then feed into whatever framework that you're using. And
yeah, basically,
there's an example, like, check out the chat demo, which is essentially a back-endless chat application which uses peer-to-peer communication between browsers and is built on React. That's an example to plug into React. On Netify, yeah.
So you see in my package JSON, I don't use anything there, but I could have added something if I wanted to. I just use this JavaScript dependency. If I look at my app.js, and I usually don't want to do that, otherwise I feel sick, but you know, for you I'm going to do it. And basically, if we start at the very beginning, what you have to do, this is ECMAScript 6 script. So you do some import. You have the JavaScript generated by protobuf, and you generate the JavaScript client. So service, RSocket PB and service PB, it's generated stuff by protobuf. Once you import this thing, you just have to declare Proteus, the equivalent of application properties in Spring Boot. You create it, and like what you've seen, basically, you pass the Proteus instance. There is no injection here, but so you pass it directly by reference to ranking service server. So you really are a server in terms of interaction, what we know, in terms of client-server interaction. So you, as a JavaScript client, can do that. And I pass this. That means in ECMAScript, I am implementing rank method. So it's like the equivalent in Java of doing @override rank and overriding and implementing this. And single is a type Facebook came up with. They came up actually with reactive stream JavaScript. They ported reactive streams from Java to JavaScript. And they invite us to override. So they have a RxJS bridge. We have a prototype of Reactor called JS in the pipe as well. So basically, then you can use a Flux in JavaScript or Observable from RxJS. Another question, maybe. Yes.
There was a mention in the previous talk that you gave at the main stage by Joe from Facebook about use of this for GraphQL subscriptions.
Yeah.
Can you go into a little bit more detail? Like, is there a custom client? Because I know Apollo doesn't support this.
I personally haven't used GraphQL, but if you want to take that question, Steve. So to repeat what the question was and Steve's answer was, the question was, can we go into more detail about GraphQL? My answer was, I'm a noob, and Steve's answer was, there is an implementation in C++ to do that. So if you go in, I guess, RSocket C++, you will see how it looks like in C++. And then I think it's a Thrift, just a C++ implementation, you should see that in the RSocket organization on GitHub.
Apollo does not support the live query functionality that Steve mentioned in the keynote. We're working on a client sort of on our roadmap within Netify to have a first-class support for GraphQL. including the live query stuff, so you could just automatically compose that together.
Live query on top of subscription. So
Yeah, that gives you the subscription behavior for GraphQL.
Yeah. Another question is, yeah, there was one, sorry.
What happens to clients if your broker fails? For example, you remember you started your app, broker wasn't performance. Is there any possibility to revive a client?
Yeah, what's actually going on there is the clients connect to a seed broker, and from there they're using the same discovery mechanism that that the broker uses to find other services, to find other brokers. So you can define a number of brokers that you want to connect to. For Java, for instance, you can have redundant connections to a broker. And if one broker fails, it will automatically redirect traffic to another broker. So there is an initial load balancing that happens from the client side to a small number of brokers. And then if you do sort of a rolling deploy, you'll get notifications of the new sort of broker cluster that's available, and it'll automatically switch traffic over.
Which makes... Yeah, correct. So there is a redundancy at the client side, and also it makes me think that it's not magically removing all the distributed system complexity you have with a client. You know, we have still a kind of a big responsibility as a client to do some stuff, but much less than HTTP, because we have the benefit of using connected, currently connected and kept alive connection. We have a status flowing over this same open connection. It's not like in HTTP where you have a disconnected experience when you request something and you get a response. You don't know if the next request is going to actually work or no, if the server, the backend is actually failing. At least with a TCP or WebSocket connection, when it's failing, you immediately know that it's failing, like in an event-driven way. You already know. Basically, you cannot connect to this server anymore, you're switching. So it's removing a bit of, if not a lot of complexity from this perspective as well.
Yeah, I think the load balancing can go a long way. So you can deploy new versions of the service in parallel with others, and the load balancer will automatically figure out which is the best experience for your user. There are cases where you might want to deploy new functionality, sort of new business logic that actually degrades the latency that people experience. So I think there's still very much a place for things like Spinnaker and Canary deployments, where you want to just analyze the traffic that's going to a new cluster before actually switching over. But it does make a certain subset of those use cases extremely simple.
Mm-hmm. I think we are a bit over time, 10 minutes, and everyone is getting hungry and angry, I guess. So thanks for sticking with us. Thanks for understanding my French accent again. And thanks, Ryan, for being there with me as well. If you have any question offline, we'll stick around. Just find us. And they have a stand as well, I think, in the community hub. So visit the Netify guys. Thank you.